Welcome to this video. In here we're going to talk about categorical variables, two-way tables, and Simpson's paradox. So what is two-way tables? It's basically the tables that focus on two categorical variables. In this scenario, we're going to focus on age and education. So take a look at the table right here. Here are the education levels, and here are the age groups. So basically, we want to grab some information from this table. And what we're going to do is basically using the value that we examine divided by the total number in that column or row and get the percentage. And relative frequency is always percentage. The marginal distribution is the breakdown of one variable. And we will go more deeper of that. So let's draw a bar graph for the marginal distribution of education. So in here, we already calculated the different education level people completed, fall into what age groups. So basically what we're doing is using the age group number, for example, we're actually using the total. So like different education level people, in here will be 27,853 divided by the total number, like the people were the survey include, or this experiment included, and get the percentage. And we're going to plot the percentage onto this bar graph. The x-axis is the college and y-axis is simply the percentage. And that's the marginal distribution of the, oops, sorry, this is not what we're doing right here. We're doing actually here, okay. Oops. Okay, sorry about that. Yeah, so this is the percentage and this is the college. And this is the marginal distribution of education. So the conditional distribution of age given did not complete high school. So things get more interesting here. We're given some conditions and we're asking to find the percentage. So instead of dividing the total, we're dividing the corresponding conditions number of people. So what is conditional distribution? It's breakdown of one variable given one condition of the other variable. So in this case, given did not complete high school, which means this will be in our denominator. So we're going to looking at did not complete high school, this total number, and we're trying to find different ages. So we're going to use 4474 divided by 27,853 people, get the percentage. Same thing doing for 35 to 54 and 55 plus. And conditional distribution of education given 55 plus. So those are basically the questions that helps you to exercise. But we didn't do it on class, so if you want to do it, feel free to do it by yourself. And what we're going to do is create a segmented bar chart. Well, what is it? It's actually pretty similar with bar graph, but instead of just doing one group or one category as a whole vertical bar, we're divided into different conditions, like different groups based on different conditions. So you can see that did not complete high school and high school certificate, or 1 to 3 years of college, or 4 more colleges, corresponding with different parts of a bar. And different bar is for different age groups. So that's the main idea for segmented bar chart. And we're gonna looking at a pretty interesting phenomena, which is Simpson's paradox. Save Aunt Mary. The following example uses fictional data. Just a little bit alert. So surgery patients. We are given two hospitals, St. Jules and Rose. We're recording the number of people, like the patients died of the surgery, from the surgery, and the people who survived from the surgery. And we're given two sample of data. And we add them up, get the total number of patients we examined. And let's construct a conditional distribution of survival rate given hospital. So the death rate from St. Jules is 63 divided by 2100, which is 3%. And Rose Hospital is 16 divided by 800, gives you 2%. From this data, it's clearly to say that the St. Jules Hospital have a higher death rate for taking the surgery. But is that really the truth? We have to do more examination from it. So something is lurk. Remember the causations from last video? We talk about some scenarios and some examples. Some lurking variables may be impacting our conclusion, deviate our conclusion from the truth. So let's disaggregate the data. So we're creating a table again. Instead of this time, we're dividing the group of patients into two categories. One is the patients with good health, and one is the patients with poor health. And then we're using the same method to get the death rate for each hospital. And we surprisingly find out that St. Jules Hospital, for the patients having good health taking the surgery, the death rate is only 1%. While for the patients who have poor health body, the death rate is 3.8%. And for Rose Hospital, for patients have good health body, having death rate is 1.33%. And for patients have poor health body, having death rate is 4%. So you can see that data is really different for depending on the condition for the patients. So sometimes the hospital's quality is not the only factor for determine if a surgery will be successful or not. Sometimes the patient itself, himself or herself, have a bigger role for doing the result. So let's collect our data, or let's summarize our data a little bit more. So for the good health, we're getting those numbers, and for the bad health, we're getting those numbers, and those are the percentage we calculated in here. So what are some things that you see from this phenomenon? Like, this is interesting, because from our previous data, we can clearly say St. Jules Hospital will have a higher death rate, therefore we won't let Aunt Mary go into St. Jules Hospital. But if we divide our calculations by groups, we can see that overall St. Jules have a lower death rate, while Rose Hospital has a higher death rate. So which one should we choose, or which one should we trust? We can trust neither, because either of those provide the whole picture. And you may think, well, basically you're saying it's just nonsense, because you definitely cannot see the whole picture. It really depends. It varies a lot. True. I agree with you. So that's one of the things that statistics is focused on. We can always, we cannot always see the picture. I mean, most of the cases we cannot. So what we're gonna do is we're gonna manipulate our method or our way of treating this data to make it closer and closer, extremely closer, like as possible as we can get to the real picture. And we want to let our conclusion be as more representative as the whole group of data. And in this case, it's hard to find out. And think about that. What are some causations, or what are some reasons that make our data so different using two ways of calculations? First of all, take a look at the numbers of patients that we collected from different hospitals. You can see that St. Jules, we collect a bigger portion of the patients, while Rose is smaller. So as bigger as our sample will be, actually the data that we drew will be closer to the real data that we want, the real value. Therefore, the St. Jules, the data may be closer to the real death level of St. Jules Hospital, but since Rose Hospital, we only drew this much of people. So it may be deviate, or maybe a little bit far off with the real value from Rose Hospital surgery. But that's only one reason. Some other reasons maybe include, like different conditions of each patient, or the time of the surgery has been held, or the level of the doctor. There's a lot of factors who will impact our conclusion. So it's always not a bad idea to approach statistics in different ways, because the more ways you did by yourself, the more ways you practiced, the closer you will get from the real truth. So I hope you learned something from this video, and I always love Simpson's paradox. I feel like it's really a good theory. it's a good way to look at things, to treat things differently compared to usual ways. And yeah, but more importantly, I hope you learned something from this video and something related to stats, two-way tables, and Simpson's paradox. Thank you so much for watching. I hope you have a great day.